Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel and today's topic of discussion is gear pumps. Our objective is to examine a common fixed displacement pump known as a gear pump. We'll examine its principle of operation and the internal components that make it function. Recall during the hydraulic pumps lecture, available at the Big Bad Tech channel, we introduced positive displacement pumps, where positive displacement pump is one characterized by a clear and definite separation between the inlet and outlet ports. The operation of a positive displacement pump can be explained using a sequence of events. First, a positive displacement pump closes an outlet port, opens up an inlet port, and provides a region of increasing volume. For a manual pump, this is the upstroke of the piston. The increasing volume forms a vacuum into which liquid at atmospheric pressure is actively drawn into. This is the suction phase of a pump. Next, the pump seals the inlet port and opens an outlet port, all the while squeezing the entrapped fluid in a region of decreasing volume. This is the compression and exhaust phase of a positive displacement pump. For a manual pump, this is the downstroke of the piston. Next, the outlet port is sealed and the inlet port is open, and the process repeats itself over and over. The completion of one full open inlet, closed outlet suction, and closed inlet, open outlet compression and exhaust is known as a cycle of a pump. For rotary pumps, one complete cycle of a pump is ordinarily one complete revolution of the drive shaft. Positive displacement pumps use close-fitting components and must properly filter and condition fluid to be pumped to predetermined cleanliness standards if they are to perform reliably. Particulate contaminants may progressively abrade close-fitting components, leading to a loss of lubrication and sealing ability, as well as hinder efficient movement of the dynamically moving surfaces. Additionally, heat-degraded oil forms a sticky resinous byproduct known as varnish that can plug ports and glue ordinarily moving components together. The fluid filtration and conditioning lecture, available at the Big Bad Tech channel, discusses these effects and the means of mitigating them. In summary, positive displacement pumps have a suction phase that actively draws in fluid and a clear and definite separation between inlet and outlet ports. Positive displacement pumps are for applications necessitating high pressure, like hydraulic systems. Three types of positive displacement pumps are commonly employed in hydraulic systems: gear pumps, vane pumps, and piston pumps. Pumps, regardless of their type, can be classified as fixed or variable displacement pumps. Fixed displacement pump, as the name implies, is incapable of varying displacement per revolution. A variable displacement pump, in contrast, uses movable internal components to selectively increase or decrease displacement per revolution as required. Gear pumps use a pair of equally sized meshing gears to provide pressurized flow to a hydraulic system. All gear pumps are fixed displacement pumps. Vane pumps can either be fixed or variable displacement pumps depending upon construction. A vane pump uses a slotted rotor and extendable vanes that scrape the inside of a cam ring. A fixed displacement vane pump keeps the relationship between the rotor and cam ring constant, whereas a variable displacement vane pump varies the position of the cam ring or rotor to vary displacement per revolution. Piston pumps can either be fixed or variable displacement pumps depending upon construction. A piston pump uses an angled plate to position pistons inside a rotating piston block. A fixed displacement piston pump keeps the angle constant, whereas a variable displacement piston pump varies the angle to vary displacement per revolution. The intention of this lecture is to examine the internal construction and discuss the principle of operation on gear pumps only. Later lectures will examine vane and piston pumps. All gear pumps are fixed displacement pumps in that the quantity of fluid introduced per revolution of the drive shaft cannot be modified by moving internal components. Flow rate is a measure of volume per unit time, and flow rate is the principal factor that influences actuator speed in a fluid power system. Flow rate is the product of displacement per revolution times rotational speed. This calculation ordinarily necessitates a unit conversion, since displacement is customarily expressed in units of cubic inches per revolution, and flow rate is customarily expressed in units of gallons per minute. Displacement is often referred to on a pump datasheet as CIR, or cubic inches per revolution. Since all gear pumps are fixed displacement pumps, this relationship suggests that the only way flow rate can be varied is to increase or decrease rotational speed using a variable speed prime mover, the classic example being an electric motor with a motor drive. As discussed in the hydraulic pumps lecture, accurate flow rate calculations must take into account two important factors at increasing pressures. 1. Decreased displacement per revolution due to increased leakage, and 2. Decreased rotational speed of the prime mover due to increased torque requirements. A graph of volumetric efficiency, or flow rate at different pressure requirements provided by the pump manufacturer, would allow a technician to predict these influences. However, if we neglect these pressure-induced complications, given a gear pump with a fixed displacement of exactly 0.5 cubic inches per revolution, driven at exactly 1,800 RPM, we would expect it to produce a flow rate of 900 cubic inches per minute, or roughly 3.9 gallons per minute. Gear pumps are simple, inexpensive pumps, and because of these factors are extremely popular and reliable for most hydraulic applications. Gear pumps can either be external, lobe, internal, or gear rotor type. However, the external gear pump is the most popular configuration and the focus of this lecture. Those interested in lobe, internal, or gear rotor type gear pumps are encouraged to seek guidance elsewhere because I am not going to cover them because you are not going to run into them. On the rare occasion you do run into them, do not let me know because I don't care. I really don't. With an ounce of determination, you should be able to figure out how these alternative gear pump configurations execute the suction and compression and exhaust sequences of positive displacement pumps. External gear pumps are characterized by a pair of equally sized intermeshing externally toothed gears. One gear is the active drive gear. The other is the passive driven gear. Besides the term drive and driven, this pair can alternatively be called master and slave, or drive and idler, among other manufacturer-specific terminology. As the title implies, the drive gear is the one actively turned by the prime mover. The drive gear is identified by being the one with a key or keyway to which a shaft can be attached. Alternatively, sometimes a drive shaft is permanently affixed to the drive gear. The prime mover, be it an electric motor or internal combustion engine, rotates the shaft, which in turn rotates the drive gear. Note, very rarely is the prime mover directly attached to the pump shaft, but rather uses a coupling intermediary. The coupling compensates for misalignment and allows a technician to take the pair apart for maintenance, inspection, or repair purposes. The driven gear, in contrast, is passively turned in the opposite direction by the meshed teeth of the drive gear. When the drive gear is rotated counterclockwise, the driven gear passively rotates clockwise. In contrast, when the drive gear is actively rotated clockwise, the driven gear passively spins counterclockwise. The drive and driven gear live inside a housing or body with two ports. Given the drive gear is actively rotated clockwise and the driven gear passively turns counterclockwise, this means the bottom port creates a region of increasing volume as the teeth unmesh. This port would therefore be the inlet and be performing the suction phase of a positive displacement pump. Oil trapped between the teeth and the housing is then brought around each gear and deposited in a region of decreasing volume as the gear teeth mesh together. This port would therefore be the outlet and be performing the compression and exhaust phase of a positive displacement pump. In summary, when this drive gear is actively rotated clockwise and the driven gear passively turns counterclockwise, the bottom port is the inlet and the top port is the outlet. This tends to be a point of confusion for most people since they incorrectly assume liquid is pulled in the opposite direction through the meshing teeth like a piece of paper through rollers on a copier or a printer. This is incorrect because liquid is an incompressible phase of matter. Liquid is sucked into the system by the unmeshing teeth and then brought around the gears and squeezed into the system by the meshing teeth. This behavior is perhaps best illustrated using an animated clip. Notice how the unmeshing gears create a region of increasing volume which fluid is actively being drawn into at the inlet port. Oil, symbolized by the bubbles, is trapped between the teeth and the housing and brought around each gear. The meshing gears create a region of decreasing volume, which pressurized fluid is being actively pushed into the system. If the prime mover were to switch direction, directional flow would also reverse. Note when the drive gear actively turns counterclockwise, the driven gear passively turns clockwise. This means the top port creates a region of increasing volume as the gear teeth unmesh. Oil trapped between the teeth and the housing is then brought around each gear and deposited in a region of decreasing volume as the gear teeth mesh together. In summary, when the drive gear is rotated in the opposite direction, the top port is now the inlet and the bottom port is the outlet. Note, not all gear pumps are designed to be driven in reverse and are ordinarily unidirectional. We'll examine the details behind this in a moment. You should be able to determine direction of flow and/or direction of rotation for one or both gears given a diagram of a gear pump in different orientations. Just saying, this might make an excellent quiz question, and only your lazy lab partner could blow something this easy. That's really all there is to the internal construction and basic operation of an external gear pump. Let's disassemble some representative examples of gear pumps and see if we can identify some of the constituent parts. Here's the internal workings of an extremely simple gear pump. There's really only two moving parts, the drive and the driven gear. For this reason, gear pumps have a reputation of being reliable, robust, and inexpensive. However, not exactly the most mechanically efficient pump, nor suited for super high pressure applications. When disassembled, note the idler gear spins on an axis internal to the housing, and the drive gear is permanently affixed to the drive shaft. When reassembled and the drive gear is actively rotated by the prime mover, the gear pump performs as we expect. The unmeshing gears at the inlet create a region of increasing volume, which fluid is actively drawn into. Oil would be trapped between the teeth and the housing and brought around each gear. The meshing gears at the outlet create a region of decreasing volume, which pressurized fluid is actively pushed into the system. In addition to the housing and the paired drive and driven gears, gear pumps have both dynamic and static seals. The drive shaft would form a dynamic seal with that of the housing, since they move relative to one another. In contrast, the housing would form a static seal between the two non-moving halves with the use of a gasket or an O-ring. These seals might be the only parts that really require routine maintenance if the pump is operated inside the recommended range with properly filtered and conditioned fluid. Here's yet another example of a gear pump. This is a Prince SP25A32. There's really nothing external to quickly distinguish this as a gear pump other than the part number. The drive shaft is visible on one end, as well as two ports on the other. The large port is intended to be the inlet, and the small port the outlet. The bolts can be removed and the port or back end plate taken off. We can take the drive or front end plate off. Note the static seals on both end plates. Inside the housing or body, we can see a bearing carrier assembly holding the intermeshed drive and idler gear. We can remove the bearing carrier assembly and wear plate. Now we can get a good look at the intermeshed gears. We can pull out the back bearing carrier assembly and wear plate, and the drive and driven gears. There you have it, a fully disassembled gear pump, truly horrifying in its complexity. The manufacturer's service manual for this particular pump includes a great exploded diagram, as well as disassembly and reassembly instructions, inspection procedures, and troubleshooting advice. Here's the housing. There's a faint tracked area matching the gear position. However, note the tracked area is smooth and there's no unusual scoring or pitting. Here's the drive gear. The teeth aren't pitted, warped, or broken, nor is the shaft bent. Same thing for the idler gear. The teeth aren't pitted, warped, or broken, nor do they show any unusual discoloration. I'm not sure if you can really see it with this picture, but the teeth of both the drive and idler gear are asymmetric, in that one side of a tooth is smooth and the other side has a tiny undercut. The orientation of this undercut is super important when reassembling this pump, as is the orientation of the bearing carrier assembly. The manufacturer's service manual includes a diagram showing the proper orientation for different rotation directions of the prime mover. When reassembled, the gears should not bind when rotated in the correct direction. The pump datasheet includes some important specifications. The SP25A32 has a displacement of 2.008 cubic inches per revolution and is rated for 3000 psi. Additionally, the datasheet specifies the permissible viscosity range and filtration level, in this case 1714. The 2-number ISO cleanliness code indicates this gear pump could essentially care less about particles in the 4-micron bin and concerns itself only with 6 and 14 micron size contaminants. The pump datasheet also includes performance data in a tabular format rather than a chart. Note the performance data is based on certain standard conditions, specifically an oil with a given viscosity and temperature, 140 seconds universal at 120 degrees Fahrenheit. Given ideal conditions in which a pump with a displacement of exactly 2.008 cubic inches per revolution is driven at increasing rotational speeds, we'd expect the flow rate to increase linearly like the ideal curve in green. When the actual performance data from the table is plotted on the red curve, the pump behaves as expected. At an increased pressure requirement of 3000 psi, flow rate is slightly reduced due to increased leakage. The theoretical versus actual performance data could be used to calculate volumetric efficiency at different rotational speeds and pressure requirements. For example, when a pump with a displacement of exactly 2.008 cubic inches per revolution is driven at exactly 1500 RPM, one would expect it to produce a flow rate of 3012 cubic inches per minute, or approximately 13 gallons per minute. However, the datasheet says that when operated at 3000 psi, the pump only actually produces 12.43 gallons per minute, or approximately 2,871.3 cubic inches per minute. Assuming rotational speed really is exactly 1500 RPM, we can solve for displacement per revolution to be not 2.008 cubic inches per revolution, but rather a slightly smaller, approximately 1.914 cubic inches per revolution due to increased leakage. Volumetric efficiency at 1500 RPM and 3000 psi is therefore 1.914 over 2.008, or close to 95.3%. Additionally, note this pump datasheet also includes required mechanical power input for different rotational speeds. This data could be used to calculate overall efficiency of the pump, where overall efficiency is the ratio of hydraulic power output for a given quantity of mechanical power input. Hydraulic power can be calculated in units of horsepower by multiplying pressure in units of psi times flow rate in units of gallons per minute and dividing by 1,714 to account for constants. For example, the hydraulic power output for a pump producing 12.43 gallons per minute at 3000 psi is approximately 21.76 horsepower. The datasheet specifies the pump must consume at least 24.22 horsepower of mechanical power input when operated at these conditions. Overall efficiency is therefore 21.76 over 24.22, or approximately 89.8%. Overall efficiency includes not only volumetric inefficiencies, but also friction, heat, any misalignment between the prime mover and pump, and or play between the mechanical linkages, among other losses. Moving on, here's yet another example of a gear pump. Note the suction strainer on the inlet of the pump prevents it from ingesting any contaminants in the reservoir that can clog the inner workings. Additionally, note the bottom plate includes an integrated pressure relief valve. When we pull off the integrated pressure relief valve and disassemble the housing, we find two equally sized intermeshing gears, where the drive gear is permanently affixed to the drive shaft, and the driven gear sits in two recessed pockets in the housing. Note these gears are helical rather than spur gears in our last example. The helical cut allows for increased contact surface area and decreased noise. Given the tiny gears, we probably expect small displacement value per revolution. This particular gear pump is actually employed for an oil pumping application, not a high-pressure hydraulic system. However, a quick look at the datasheet serves our purposes quite nicely. This particular pump is a Rickmeyer R25 2.5, where 2.5 means it has a displacement of 2.5 cubic centimeters per revolution, or roughly 0.153 cubic inches per revolution. It's super tiny. The common place of the decimal point is kind of a European thing, like fast trains, free healthcare, and smoking teenagers. Note the datasheet is written in both German and English. Don't be surprised one day when you open up the box housing a new part and find a datasheet or instructions written in a language you can't read. My advice is to deal with it. Numbers and charts are universal, and you should be smart enough to interpret what you see. The units might be a little odd for those cave-dwelling savages that don't use the metric system. However, a simple unit conversion should do the trick. The flow rate versus pressure graph looks exactly like the curve we examined in the hydraulic pumps lecture. Given a nominal drive speed, as pressure goes up, flow rate goes down. This behavior can be largely explained by increased leakage and the tendency of the prime mover to rotate slower given increased torque requirements at higher pressures. Note pressure differential between the suction and pressure connection is expressed in units of bar. Obviously, this pump isn't meant for super high pressure applications since the curve ends at 10 bar, or roughly 145 psi. Flow rate is expressed in cubic decimeters per minute, which might seem odd at first until you realize a cubic decimeter is actually a liter. This unnecessary coyness with the units kind of makes me want to punch this datasheet in the face, but I am not going to win any hearts and minds raging about proper units given my country of origin uses gallons, circular mils, degrees Fahrenheit, and half the population doesn't believe in dinosaurs, yet they do believe in angels. The struggle is real. Regardless, flow rate varies from just high of maybe 3.6-ish liters per minute to just low of maybe 2.7-ish liters per minute inside the recommended pressure range. Note the chart is again based on certain standard conditions, particularly a nominal drive speed of 1450 RPM and a liquid with a given kinematic viscosity of 33 square millimeter per second. Again, the viscosity units are unnecessarily coy since 1 square millimeter per second equals 1 centistoke, another common viscosity unit. 33 centistokes, by the way, roughly equates to a liquid with a viscosity of 155.7 Seybold seconds universal, roughly that of hydraulic oil. Allow me to step out of pump world and briefly comment on the prime mover. Note the nominal drive speed, 1450 RPM, is characteristic of a 2-pole pair per phase squirrel cage induction motor operated at 50 Hz, as is common in the EU, not the 60 Hz standard employed in the United States. A 3-phase AC system at 60 Hz might see a 2-pole pair per phase squirrel cage induction motor rotated around 1740 RPM, thereby skewing the flow rate curve upwards given this is a fixed displacement pump operated at increased rotational speed. Lectures on motors and generators will discuss how pole pairs per phase and excitation frequency affect synchronous speed, the speed of the rotating magnetic field for 3-phase AC systems. Additionally, the datasheet for this pump family lists the permissible viscosity range, permissible degree of contamination using the ISO cleanliness standard, in this case 21, 19, 17, as well as temperature ranges for 2 available types of seals. Before we bring this lecture to a close, as much as I'm about to roll my eyes right out of my sockets, in the interest of thoroughness, I should at least briefly introduce lobe, internal, and gear rotor types of gear pumps so you can compare them with external gear pumps. External gear pumps, as the name implies, are those pumps characterized by gears with teeth radiating externally away from the body, like the spines of a porcupine. A lobe pump, for all practical purposes, is an external gear pump, except it uses rounded lobes instead of angular teeth. If you know how an external gear pump works, you know how a lobe pump works. Internal and gear rotor type gear pumps, in contrast, use internal gears, where the teeth radiate inwards like the teeth of a shark. Both these types of pumps feature a rotating, internally toothed gear surrounding a rotating, externally toothed gear, kind of like a shark eating a porcupine. The internal gear pump uses something called a crescent seal to create a seal between the offset gears, whereas a gear rotor pump does not have a crescent seal and instead relies on a rotor with one less tooth and an offset port plate to positively separate the input and output. Here's the inner workings of a gear rotor type hydraulic motor, where a hydraulic motor is essentially the opposite of a pump, being an actuator that produces rotational mechanical power when supplied fluid power. Note, external gear pumps have a reputation for being extremely tolerant of less than clean fluid because of their relatively simple construction. After all, there's really only two moving parts, the drive and driven gear. For this reason, external gear pumps are reliable, robust, and inexpensive. However, not exactly the most mechanically efficient pump, nor suited for extremely high pressure applications. Later lectures will examine vane and piston pumps that exhibit notable differences in construction, operation, and performance. Until then, that's all I've got for you. In conclusion, this lecture discussed a common fixed displacement pump used to provide pressurized flow to hydraulic systems, known as a gear pump. We discussed the concept of operation, examined the internal workings, identified constituent parts, and looked up pertinent data on a datasheet. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.